Hello, everybody. Thanks for coming back from that from coffee. I'm supposed to talk today with Steve Tadelis, who's here, about some of the applications that have been going on in the field of market design. Some of you may not know, but basically one of the things that the IT revolution has done, as you know, in the web, is that many more markets are conducted on the internet, and the rules get coded, and people care a lot about what those rules are, and those things do affect the performance of markets. And perhaps would be more appropriate to call this machine learning in market design, because so far many of the things that have been done, and the things that Steve and I are going to talk about, are how machine learning techniques have been used to improve the design of markets. I'm going to give you one rather longer, detailed explanation of the recently completed U.S. incentive auction, which depended deeply on these things, and then Steve will tell you about some other online applications. This is, again, really about machine learning and the incentive auction. And for those of you who don't know what the incentive auction is, it just finished in April of this year. It began the Obama administration, the U.S. National Broadband Plan in 2010 noticed that there was a growing demand for radio spectrum capacity for broadband and related services, shrinking value of licenses used for over-the-air television broadcasts. More people were watching television from satellite and cable. In fact, by this point, it was something like 95% of the U.S. population had coverage from cable or satellite. So the hypothesis was that it would be efficient to reallocate some of the channels, some of the spectrum, to mobile broadband. That turns out to be a massive coordination problem involving coordination among thousands of TV stations, shifting channels, and clearing the spectrum all in a way that's more or less simultaneous so that we don't get radio interference. And it's essentially a collective action problem. It involved international and interregional coordination of uses. There were treaties renegotiated with Canada, cooperative agreements made with Mexico, zoning-like restriction on adjacent uses. You can't have television broadcast in one channel and mobile broadband on the adjacent channel, so that needed to be coordinated. The band plan, which bands were used for uplink and which were used for downlink, depended on how much bandwidth was going to be available to reallocate it, and that depended on the market outcome. So this was a complex reallocation process, and all these changes needed to be made simultaneously, so it needed to be planned, because otherwise you'd get lots of interference during the transition. What actually happened, it ended in April 2017. There was a lot of spectrum cleared, 84 megahertz, 70 of it used for mobile broadband and 14 for unlicensed uses. It was about $20 billion in gross revenue from the sale of the mobile broadband licenses. Broadcasters, there were 175 broadcasters that agreed to go off the air. They sold their broadcast rights for about $10 billion in this auction. The highest price for a single station was a station in Chicago, $304 million. My own local public television station got $95 million for one of the 3 channels that they broadcast on. So this was a big deal for the broadcasters and for the mobile industry. The reason that what made this unusually complicated as a resource allocation problem was the kinds of constraints on radio spectrum allocation. So this is an example. There's one TV station here, and I think this is New York City, and each of the pink nodes in this diagram represents another TV station with which it potentially interferes if they were to broadcast on the same channel. So we create a graph here in which each node represents a TV station. Each arc represents an interference constraint that says those 2 stations can't be on the same channel. There are about 130,000 constraints like this in the US reallocation problem, and so this is a big problem. Turns out that the co-channel interference constraints aren't all of them. If you list, sometimes channels that are stations on adjacent channels might interfere. So it turns out when you list the whole thing, it's about 1.5 million constraints that are relevant. And if you used only, the question you want to ask yourself, ultimately we took channels 14 to 36 and left them in TV broadcast and cleared the higher channels. So if you had only those channels 14 to 36 available and you have a set of bids, is it possible to assign the remaining channels to the remaining stations to these channels without creating interference? That is, for the mathematicians here, that's a graph coloring problem. It's the same as the question, can I put a color on each node in the graph so that no two connected nodes are the same color? It's an NP-complete problem. There don't exist algorithms that are guaranteed to be fast for such problems. And in the actual auction, we had to answer this question about 75,000 times, or about 75,000 combinations of bids that had to be investigated. There are 130,000 of these co-channel interference constraints. If you actually listed out all the potential constraints, there could be as many as 2.7 million. We didn't actually, not all of these were actually binding, but there were 2.7 million. So this is a large-scale NP-complete problem for which there don't exist any algorithms that guarantee that you can even check whether a set of bids is feasible to accept. And what I want to talk about is, oh yes, first of all, for the economists here, the first proposal that was made by the insiders was we should run a Vickrey auction and do a combinatorial optimization, find out what the efficient allocation is based on the bids, pay everybody their Vickrey price. That should work. Turns out that Vickrey prices aren't even computable in this setting. If this is the formula for a Vickrey price, the economists all know it. The rest of you, this is the formula for a Vickrey price. It's the difference between the solution of two optimization problems. These optimization problems, the FCC, after spending a lot of time with Gurobi and Cplex, discovered it could probably solve them to within 3%. If you make even a 1% error in one of these problems, that's 1% of the grand total. There's about 2,000 stations. So that means your pricing error is about 20 times in each, for any one station, is about 20 times the value of an average station. So even if we could do this to within 1% accuracy, you couldn't run a Vickrey auction in this context. So we needed to do something that adapted to the complexity of the situation. And just for fun, a little bit more problem with the complexity. Imagine we're doing this in 2011. Imagine we're trying to get TV broadcasters to participate, and we write this letter to the broadcasters. Dear Mr. Broadcaster, we've heard your concerns about the complexity of the spectrum reallocation process. You may even be unsure about whether to participate or how much to bid. To make things as easy as possible for you, we've adopted a Nobel Prize-winning auction procedure called the Vickrey auction. In this auction, all you need to do is tell us what your broadcast rights are worth to you. We'll figure out whether you're a winner, and if so, how much to pay to buy your rights. The rules will that ensure it's in your interest to report truthfully. That's the magic of a Vickrey auction. The computations we do will be very hard ones, and we can't guarantee they'll be exactly correct. Also, the federal law forbids us to share the information. You'd need to check them. We thought this might not fly. And so the details about the auction design that we adopted, which is supposed to be obvious to the bidders, and the bidders seem to believe was obvious, is in a paper that in the Proceedings of the National Academy of Science that Kevin Leighton Brown and Elias Segal and I wrote. But I don't have time to describe the whole auction design today. Instead, I want to talk about the computations and the role of machine learning in making this whole thing possible. So what we did is we wanted to do better on feasibility checking, given that there don't exist any algorithms that, in worst case, do well. We wanted an algorithm that on the actual problems we would generate in the auction would do well. And could you find such an algorithm? We used machine learning to identify an algorithm that would work well for this problem. So this is all work done by Kevin Leighton Brown's lab. He's at the University of British Columbia. The data we generated between November and February 2016 using the actual interference constraints and an auction simulator with simulation assumptions that I won't have time to go over, but were believed to be realistic. Thank you.
That includes my time.
Okay, I'll go real quickly then. We generated 1.4 million instances. We took the best commercial software. We tried, this is Cplex and Gurobi, and you can see that in a run times of up to 100 seconds, they were solving only 10-20% of the problems. We tried logical engines. We applied a configurator, which basically varied the parameters of the, did machine learning. I'm going to just make this real simple because I have to go quickly. Machine learning on the parameters of the simulator. This is the details of the machine learning, but I have to leave time for Steve, so I'm going to skip the details of the machine learning. The ultimate result was this performance on the simulated problems. Remember that Cplex and Gurobi in 100 seconds could only solve about 10 or 20% of the problems. After applying machine learning and the other techniques, which I don't have time to go over, we were able to solve about 99% of the problems in that period of time, most of them much faster. In fact, the median run times were taken from about 6 minutes down to about 1/7 of a second by these techniques. It's just amazing. It was my first experience with machine learning. We then took these and in our simulator ran a hypothetical auction to see how our alternative auction design would work using this technique, again, without being able to use Vickrey. And we took a reduced problem that we were able to solve with Vickrey, which would have taken 108 hours. The solution, our algorithm took 7 minutes to run the auction instead of 108 hours. And I guess I have to leave time for Steve. I'll just tell you that the performance in the simulations was really quite spectacular. We were getting efficiencies in excess of 99%. And we also had, using the scoring techniques we were using, we brought in ideas of optimal auctions from Meyerson in terms of identifying how the prices were set. And we have about a 25% cost savings relative to a Vickrey outcome as well. Steve, I think I better let you take over here.
Okay, thanks, Paul. I really want to thank the organizers for inviting us. The room is impressive and so multifaceted. And yesterday night I was already excited because I know at least I'm going to go away with a nice pair of socks for those who are staying at the hotel. But now I'm going away with much more. I want to spend a little bit of time, probably about 8 minutes, 7, on how marketplaces are changing the way they're managed using artificial intelligence, machine learning, deep learning, call it what you want. I hear that in the other room there's a sociology conference on jargon use of new methods. So I'm going to basically take 3 very simple examples of work that I've been exposed to doing myself with others, both in and outside of corporations. And that's how marketplaces are managing the issue of matching buyers and sellers. If I take some of the issues that came up here when we talked about measuring, consumer surplus that Joel raised, the fact that we could go online now and basically do so many more things relies on the fact that we trust that we're going to get what we want and get solutions to our problems, be it as mundane as just having the right thing delivered to our door within a reasonable amount of time. And in these anonymous marketplaces, we're matched with a variety of people from all over the world. How is this even working? How is it that we're relying on these anonymous large-scale markets at a time that this technology is developing? And one of the things that many believe has been a big lubricant to these online marketplaces has been measures of seller reputation or product reputation. The fact that I could read some kind of review and say, you know what, I trust this market. okay? Unlike, not unlike what happened, again, mentioning economic history in the trade fairs of Europe, where you had institutions that created trust. Because without trust, you do not have transactions. So in particular, these feedback systems are there to say, okay, you could buy something from this seller because they're good, but anyone who's familiar with these online marketplaces, the grade inflation has been dramatic. So just as some numbers, the median percent positive of a seller on eBay is 100%. Okay, that's not really helpful, okay? So the question is, how could the marketplace use behavioral data to measure the quality of a transaction, data that they're actually accumulating as part of the process of trade? Some refer to this as, the exhaust data. It's just happening in real time. So in particular, we've been involved in some ways of taking natural language processing, one of the applications of machine learning, AI, and saying, how could we look at messages sent between buyers and sellers in order to infer something about the quality of the transaction that simple feedback doesn't seem to grab? And what we did, we started with something very, very simple. Think of it this way. If I'm buying something from Chad, you could see how ahead of the transaction I might want to ask him something. Oh, I noticed the color is a little bit off pink, and I'm looking for, shiny pink. And then Chad would reply saying, no, it's my camera, it really is shiny pink. So ex ante, I could see that I have a reason to engage in conversation, to learn something about the product. Ex post, after I got it and opened the box, if I'm writing him an email, probably something's wrong. So just by looking here at transactions, here you have no messages. Messages, I'll tell you about negative and neutral in a second. Then practically, given measures of how satisfied customers really are, you see that only about 3% of customers are unsatisfied when they don't send messages. If they send any message where we can't even identify negative words, the amount of dissatisfaction goes up to close to 15%. And when we could identify words that say something like, where is it? It seems broken. You're a schmuck. Right? If you take any of those words, it turns out that measures of dissatisfaction go up to about 30%. So a marketplace could gather these metrics and actually create indices of, as a seller, do you have a little bit of crappy messages or do you have a lot of crappy messages? How negative of an impact is that creating on the marketplace, and how are customers exiting because of that, and what are the costs of the marketplace? So this is something where you could slam AI onto a marketplace and start learning something about the lubricant that you need for that marketplace to operate. A second example in a different, so this is done using data from eBay, by the way. I had the good fortune of collaborating with a couple of scholars in China where we have data from Taobao, and they did something very ingenious. So another problem with feedback is, how do you get people to leave feedback? Because I would hope that most people in this room, being good economists, don't leave feedback. Right? Because it's a cost to you and it's not a benefit. Fortunately, many people do leave feedback, but not enough. How could we solve this free rider problem and get people to leave more feedback? Well, what they created was a marketplace for feedback where they let sellers pay buyers to leave them feedback. Now, you might reply saying, wait a minute, okay, now it's going to be rigged, I'm paying for positive feedback, but they had something clever. The reward to the buyer was actually managed by the marketplace. So the seller didn't decide when the money goes to the buyer. What Taobao did is they said, seller will commit to pay for feedback. We decide when people get the feedback. And the way they decide whether people get the feedback was based on the quality of feedback as measured by a natural language processing ML model that says, is this feedback informative about this product? And now the key was to get more feedback, not to get biased feedback. And it turns out that that really happened. And what you could see here, we have measures of effective feedback. With that rebate, you had a lot more feedback than without the rebate. But at the same time, if you look at the bias of positive or negative, you had the exact same ratio of positive. So it didn't skew things, it just created more informative feedback that then you could use. And one of the nice things is putting back your economic theory hat, if you will. Well, what kind of buyer should pay for feedback? You could think of a parallel of this to an old literature that was started by Nelson on the economics of advertising. Paul has a nice paper with John Roberts on this, where if I believe as a seller that you're going to leave me honest feedback because the system is going to measure whether this feedback is relevant, then who's going to be willing to pay for feedback? Well, if I think I'm going to get shitty feedback, I'm not going to pay for it. So only good buyers are going to pay for it, so you get an extra kick to solve the cold start problem by allowing for a signaling model in equilibrium here that actually seems to work. The last application I want to touch on is on personalized search. So again, using eBay data, we played a lot with search, and several people in the room, Hal, Susan, many others, have looked at a variety of issues related to search. And one of the things that's interesting about search is you have two things going on in parallel. Okay, so I might go to Amazon or eBay or Taobao and search for polka dot socks creative destruction, and if it's any good, I'm going to get exactly these socks. That's a very targeted search. Sometimes I might search for fashion shirts, young men, because I'm at a stage in my life where I might want to look young again. In which case, I don't know exactly what I'm looking for. So that's more exploratory. What marketplaces can do using machine learning is look at past behavior of myself and other people, do these kind of matchings, right, and classifications, and identify what kind of group I might belong to, and give me tremendous utility, going back to Joel's point earlier, of you're making my life easy. I don't have to go to the fucking mall and spend 3 hours walking around stores. I could do this in front of me now in 15 minutes and get a pretty good idea of what it is that I want. Using a somewhat facetious example is that back, I think it was 2 or 3 years ago, someone might remember exactly, when Orbitz was caught, quote unquote, by charging higher prices to Mac users than to PC users. I don't know if you remember that. It wasn't quite what they were doing. They were not charging higher prices. They were showing Mac users more expensive hotels. Right? Now, they might get a cut of the share and that makes more profits, but you could think of the other ways like, no, I want more expensive hotels. I want to stay in these shitty places. I want to stay in nice places. If that's correlated with me using a Mac, then obviously it is welfare enhancing. So there are further topics, and you know, I apologize on behalf of myself for sure. Paul and I just got caught up in a perfect storm and didn't manage to produce a paper in time. These slides are listed online. But I do want to close as my last minute, not so much with these, but going back to what I said at the beginning, that sociology conference in jargon. Some of you may know Ecclesiastes chapter 1, verse 9, all that has been will be, and all that has been done will be done. There's nothing new under the sun. There's a lot of hype on AI. Okay, and Ajay started with a paper coming out of Toronto. That's about 10 years ago, if I remember correctly. Well, here's a book that I haven't read. I hope that maybe some of you have seen this, by Hal White, who is no longer with us, as many of you know, that was published in 1989. It's a paper out of a book, Learning in Artificial Neural Networks from a Statistical Perspective. A lot of these AI stuff, right, have been around for a very long time. I'm not arguing that this is not a general purpose technology, but it's a tool at the end of the day. And the use of this tool is just going to be as good as the questions that we pose to use it. So, you know, I love the ambition of some of the earlier papers, measuring things at the economy scale and so on. And I'm down in the weeds, like, how do I take a marketplace and just make it work a little better using these tools? That's how I view these, as tools that we could implement to, you know, reduce some of the friction, create some new ways of doing old things. So, thank you.
Okay, thanks very much. Matt, now?
Actually, while they're saying it, I'll say something about this quick. So I'm econometrician, statistician, machine learner in my background, and I've been thinking a lot about how I translate what deep learning is versus what neural nets used to be. And I think for the econometricians in the room, I don't see many of you, I see Susan, but I think that Hal thought about neural nets, and the people working with neural nets back then thought about them as non-parametric learners. Nowadays, we're really thinking about them as semi-parametric learners, and we're getting very good at the parametric bits for certain types of data. So when you imagine a deep net, you should not, I mean, Hal's book's fantastic. I use it, I cite it all the time, but that material doesn't translate to the way deep nets are used these days. Okay, so I think that's that. Okay, and so in addition to being an econometrician, I also work now in AI. So I sell AI. I head economics and data science for what's called the Business AI organization at Microsoft. So this conference is fantastic. I've been struggling, thinking about framing many of these issues. What types of good is this? How do I package it? How do I contract against it? All of these various things. So this is massively, massively helpful. Also, it's very nice to discuss Paul and Steve, even though they didn't send me a paper and then ended up talking about two different topics. I don't mind at all. It's totally cool. So I tried to foreshadow a little bit what they would be talking about, and I think I kind of nailed it. So Paul and I share a co-author in Kevin, so I was able to do a little bit of Sherlock Holmesing. So I don't know if I can get rid of that finger somehow. There we are. Okay. So I really like this application because that's what it is. The earlier papers this morning were talks about ML. Okay, or about AI and what are the economics of it. Paul's in a scenario where he had a task which was, an optimization, a huge pain in the ass task, which he said, look, the computers can do that for me better. Okay? This is an economist using ML the way that we're saying it's going to disrupt industries, it's going to disrupt businesses. Okay? So I want to just I'm going to narrow in. I'm not going to talk much about the auction stuff because I don't know much about it. And I'm going to narrow in on kind of how ML was used there and use that example to make some broader points about sorting out some of this jargon of ML versus AI and data collection, all of these sorts of things, okay? So market structure's given, right? The sort of auction, what we should be doing, right? The insiders knew it right away. They said, hey, you should do this. Of course, that wasn't practical, so they replaced that with a heuristic, okay? It's this clock auction, which Paul didn't describe, and I won't describe either, but it's fairly straightforward. You can think of a sequential auction where people can opt in or out at different points with falling prices. The ironic thing is that you need to check feasibility, and that is infeasible, okay? So you cannot easily check the feasibility of solutions as you're making decisions as this auction winds down, okay? So what you have to do is you have to somehow have algorithms that can get you close to the solutions of feasibility quite quickly. And that's the hard part because there's a huge number of algorithms. And moreover, don't think of a huge number of completely different algorithms. Think about a set of, say, 6. I actually don't know how many it is, but half a dozen algorithms parameterized by thousands of parameters, right? Which can take spaces all over the place, and they have all sorts of conflicting boundaries, things like that. So really what you have here is a problem where you'd like to tune these algorithms, which are general purpose algorithms, to work well on your very specific task here, which is checking feasibility for spectrum auctions, okay? And so what happens is, this is what I inferred you guys did. I think that's actually what happened, is a version of what we call nowadays Bayesian optimization. It's one of these good ideas that gets named every few years. You loss function to minimize. In this case, I don't know whether it was time to check or whether it was the quality of the solution under a fixed time constraint, but there's some loss function out there that you want to minimize, okay? You're going to use machine learning regression. In this case, I believe it was random forest, but it could be a Gaussian process, could be a deep net, anything that has uncertainty quantification with it. That's an important point. Uncertainty quantification is key for these algorithms to predict that loss surface from the tuning inputs. So now, remember I said algorithms, huge number of parameters. What I'm doing is I'm predicting how long they're going to take to solve the spectrum auction at different parameter configurations. But instead of running the algorithms at all of those different parameter configurations, you're building a regression surface. Okay? So you're predicting how well your algorithm is going to work as a function of the tuning parameters, the same way that you would predict what air temperature is going to be as a function of all of these various inputs, sea surface, all of this sort of stuff, okay? Then what you do is you choose new inputs x to maximize the expected improvement, which is what Paul said, okay? Expected improvement is this function here, okay? So you want to minimize your function here. You have your current f min, which I also call f0 by mistake. And what you want to do is you want to have something that you want to maximize something that's either the gain you get at that new location or 0. Okay, so this is this classic, if you've talked to machine learners and people in reinforcement learning, you've heard the term explore, exploit. So I'm going to look at places where there's a lot of upside potentially, but I'm not going to penalize my algorithm if it looks out somewhere where, hey, it turns out that wasn't a new best parameter input location. That's fine, okay? This is just good utility theory, good decision theory, right? When I'm looking for new locations, this is my utility function or a heuristic utility function that works pretty well. The key point here is that Paul is in the business of collecting data, right? Which goes to something that Hal said and which Susan said, which is that the data that's out there is great, and that's great to hot start your algorithms, hot start your AI. You have to be active. Good AI systems are active about accumulating new data. Where do I look next? Where do I add things? So that's kind of how I see this. So now, going up from the specific application of ML in Paul's problem, more generally, how do I see ML and AI? How does that break down as a good? Okay? I'm going to go from right to left here. So I make a strong distinction between AI and ML, and I think it would be useful if others did as well, because these two things are different. Okay? So these are the pieces of AI. The first one here is fast machine learning, fast, cheap, whatever you want to call it. Okay? So the deep neural nets are our fast, multi-purpose, general-purpose machine learning. Okay? A point that's been highlighted, which I'm actually really impressed people here latched onto this, because I think this is the defining characteristic of deep nets, is their general purposeness. Okay? So the point was raised earlier, why is statistics not a general purpose technology? Why was ML not a general purpose technology? Well, because it took a statistics PhD to apply those things. It took a machine learning PhD to apply those things. Right now, it still takes a deep learning or computer science PhD to apply deep learning stuff at the sort of like very cutting edge. But this stuff is getting commoditized. These are very much like Lego pieces that you can put together. So the general purpose technology here, I would venture, is not AI as a whole, but rather it's the fact that the ML, the predictive pieces, are now becoming general purpose. Okay? And so that's why a little bit of the paradox, we have these general pieces of ML, and the end-to-end of AI we're just starting to figure out. Okay? And we haven't figured that out yet, apart from some specific examples like search, right? Search is an end-to-end AI where that's been figured out. The other thing is that they can deal with very flexible data input, so you don't have to do the structuring of your data, which economists are used to, which again goes to the general purpose type nature of these things. The next thing here, which is super important, and I really want people to think about, is data generation is a key piece of ML, okay? Or sorry, key piece of AI. Right? So reinforcement learning, active learning, that's the type of, what Paul did is a version of reinforcement learning, okay? As Jan said, there's a ton of things problematic with current reinforcement learning platforms, and I'll touch on that in a second. Massive sensor networks, also simulation, the idea that you can use one model, machine learn model perhaps to simulate data for another one. Paul was simulating from the spectrum auctions and stuff, okay? Finally, and this is the piece that I think is really missing, I named this in terms of our own field here, but we need a way to take these two things and put them in places where they solve actual problems. Paul's was an example of that. There are others examples of that. But the piece that's missing, the piece of the end-to-endness that's missing right now are these bits here. So I think I'm out of time, so let me just say, I won't talk. There's another really good paper, by the way, which I read because these guys didn't send me a paper, on optimal auctions through deep learning. If you're interested in this area, this is David Park's stuff. They actually, they sort of automate not just the optimization of the market design, but the entire market design process itself. And it's the first compelling application of that stuff I've seen. Okay? The final thing that I want to say in the spirit of kind of research questions is, in AI, remember I said, you have to track what worked and what didn't work. That's the reinforcement learning thing. What Jan pointed out, what others pointed out, is that right now these reinforcement learning algorithms are really focused on short-term rewards. So they're good at learning, if you drive the car into a tree many times, stop doing that or something like that, right? In business environments, in economic environments, the rewards that you actually want are long-term things, and you're not going to get the signals fast enough, and the signals are going to be confused. And so what you have to do is you have to think about how you map from an array of short-term signals that are readily available to these long-term rewards that you're actually interested in. And that's essentially 90% of my day job right now, is thinking about that mapping right there. And I think economists have a big role to play because we use economic structure to do that map. Okay, so that's what I am. Thanks.
Okay, thank you. Comments and questions? Yes, please.
So thanks so much. Those were great presentations. So I want to maybe reiterate a couple of things Matt said, maybe in slightly different language, because I think they're so important. Actually, this last point, also 90% of my day job at Bing for several years was trying to figure out how to measure the systems in a way that the short-term metrics actually pointed things in the right direction. And so there's actually this big macro consequence of this new technology, which is that machine learning needs quick rewards, fast measurement, and you in principle can innovate very quickly and test very quickly. That only is operational if you have short-term metrics. And so every single tech company drives in the wrong direction. Every single tech company has engineers working on things that look good in the short term and bad in the long term, and they completely leave the other things open. So another business I was in at Microsoft is doing all the things that looked good in the long run and bad in the short run because they were very profitable and nobody would work on them. And so that's, I guess, another way to put this is that the metrics of an A/B testing platform are an incentive system for your engineers and business people, because if you can't get your thing through the A/B testing platform, it doesn't ship. If it doesn't ship to consumers, you don't get a bonus. So it is an incentive system, and it has very particular features. I actually go back to Milgrom multitask, that basically, like, there's some things you can measure well. So the optimal incentive scheme puts more weight on the things you measure well, but then you drive in the wrong direction. And John Roberts and I have a paper about that in Papers and Proceedings like 15 years ago. The second point about incentive systems is actually when you step up to the marketplace level, the machine learning systems are the incentive system for the market participants. So I work with two marketplaces. One is HomeAwayVacationRentals.com, owned by Expedia. The other is Rover, which is dog sitting. In both cases, you have really a hard incentive problem to get the buyers and the sellers to do what you want them to do, to answer emails, to make their availability clear, to have accurate listings, and so on. And so what you use is you use the sort order as an incentive to get them to do the right things. And you rank them high if they behave well, and you rank them low if they don't. Now, and the sort mechanism is a machine learning algorithm, but it's also an incentive scheme. You're trying to match and incentivize at the same time. The machine learning people don't often understand that it's an incentive scheme, and that's where the economists come in. So then, and actually Google News was mentioned earlier. Catherine Tucker and I both have papers about Google News. You can read about that. That's another example where sort of the sort order and the way that the Google News interface looks provides incentives for news providers to create news, and it changes their incentives in terms of the getting flashy headlines versus substantive news reporting. So of course there are long-term implications of that for the market structure. Finally, one thing that Matt said at the end, which I also just want to reiterate, is that machine learning versus AI, I found that the computer scientists were much, much better than anything I could ever do at doing the straight prediction, but gosh, were they bad at putting the whole system together. And the idea you get in the newspaper that, like, we're going to have these complicated systems and they're all going to work is just crazy from what I've seen. You know, we would blow 10 million here, 10 million there, with people not understanding feedback effects, not understanding general equilibrium, not understanding that, you know, if you test on 1% of traffic, that's not the same thing is going to happen if you release something to a whole marketplace. But the science of doing that is actually super hard. But if economists and other domain experts in the room, I promise you that what you learn as a PhD in machine learning prepares you nothing for that process.
Okay, thanks for that, Susan. Hal?
I want to make a bibliographic note of Hal White. The history here is that there was a lot of attention back in the 80s on the single-layer neural networks. Papert proved that they really had severe limitations in what they could approximate. And then Hal White and his colleagues Hornick and Stinchcomb came out with this great paper that's titled Multi-Layered Feed-Forward Networks Are Universal Approximators. And so that showed that, hey, all you had to do was add another layer to these networks and you could get a tremendous improvement. That has 14,481 sites on Google Scholar, so it was really a major advance in terms of understanding what you could do and what you couldn't do with the neural nets. And one point on what Susan just said, the way to think about this is lots of experiments involve changing the interface of something. And the general rule there is you change the interface, humans will respond in minutes. Our own systems will respond in days because they have to learn there's a change. And advertisers respond in weeks or months. So you've really got this interaction of three different speeds of adjustment going on, and what you said is exactly right, that if you only focus on the short term, you're going to make big mistakes. So you have to have a model and an understanding of how these other systems are going to react as well to make any progress.
Okay, thanks for that. So Shane, and then back to the authors if they have any response.
Just a quick remark. I was struck by the differences between this talk and the prior ones. All three had as a similarity that they focused on how a reduction in cost in some process permitted a new capability to emerge that had previously not been possible. So that that was in common. And then they went to different places where we previously heard about about business process innovations. This talk was much more about coordinating innovations, coordinating behaviors in particular, and then Steve in particular about what we would have called a couple decades ago a transactions cost of a market. So just a remark that that's introducing a different way of looking at the consequences and maybe suggesting you bridge that gap a little bit more.
Okay, thank you. The authors have any response?
Thank you for those comments. I especially appreciate Shane's point about reducing transaction costs. Thank you. Which is, one way of thinking about what that does as far as the world that I'm interested in, is taking these anonymous, large-scale marketplaces and actually helping make them work, both in terms of fostering trust, but also in terms of better matches between the preferences and needs of buyers and the ability of sellers to meet those needs. And I think, what's key here for me is seeing the way in which this innovation proceeds, right? If I go back again to some of the things that Joel mentioned about, layer one, you had these steam engines, and then later it was introduced into transportation and then into production. And someone has to come up and say, oh, I could apply this too, because it's a general purpose tool, right? So this idea that we had about using natural language processing to go through the messages that people send and try and detect some sentiment that actually has a meaningful economic value. I mean, I don't know how we came about it, and it happened 2 years ago. It could have happened 2 years from now, right? So I think that one of the things that to me is most mysterious is how do people pick up on these new tools and then realize how they could be implemented in ways that were not done. So.
And Paul, did you have anything else? Okay.